are a very great hazard here in the Himalayan mountains, but also in Iceland, where I've been working on outburst floods like that. And here in the literature in India, it's often called GLOFs, G-L-O-F, GLOF. And we have a special name in Iceland for this. This is Jökullaup. But anyway, what this means is a sudden outburst of water. Yesterday we talked about how water is transported through a glacier, and typically it's moving rather fast down to the base and along the base, and somehow, and then into the rivers, and that's all. But in some cases, the water may be accumulated in the glacier, not moving as we all the time, as we talked about yesterday, but accumulating into sometimes subglacial lakes. There can also be lakes on the surface of the glaciers, and there can be lakes in front of the glaciers, which are the most common type here in the Himalayas. And we can classify or distinguish between several types of lakes. We can have subglacial lakes. They are, as the name is telling you, located underneath the glacier. They can be located in depressions in the ground, and this is the case for many of the lakes in Antarctica, which I mentioned to you yesterday. Yesterday I mentioned that 124 lakes have been detected by observations of changes in the surface elevation of the lake. So the water is accumulated underneath the glacier, and the surface of the ice sheet is rising up and down, and they are active. 120 of them are active and then I mean that they are delivering occasionally water, so they are draining out in outburst floods water. This is quite a new information about Antarctica, and has been collected only in the last few years, and by satellite altimetry and the satellite ICESat. And so this is a very exciting information that many of them are, there are many lakes collecting water. I mentioned also that there are about 280, which is much more than the 124 active ones, which are located there, and or detected under the Antarctic ice sheet, and they are all in depressions like that. But there are also lakes under ice sheets or glaciers where the water is accumulated in a water body which is rising above the surface. So you don't need a depression in the ground or hollow in the ground. What you, in this case, need is a depression in the surface instead. So if you have a depression like that in the surface of an ice cap or ice sheet, then water may be accumulated underneath that depression, and the reason is that the pressure at the bed is higher all around the depression than it is in the center of the depression. So the pressure here and there at the base, the water pressure is higher than it is here in the center. So water is moving towards this center and accumulated in a lake, in a water body which is able to rise like that above but the necessary condition for this is a depression in the surface. And so those are the two types of subglacial lakes. In Iceland, we have geothermal heat melting the ice in a few places, and by melting the ice, we are creating depressions in the surface of the glacier. First, because the ice changes to water and the volume is 10 times less as water than it was as ice. So that is, then you have a depression formed. But then you can also drain some of the water away in outburst floods, and then you will get a still deeper depression. So I will show you some examples of that. Then we have marginal lakes, and they are located at the margin of the glacier, not entirely subglacial as we say here, but at the margin. And yet this is ice, and then you have a lake at the margin of the glacier. Well, yes, okay. I will just, and then I'm talking about a lake like that. Here is an outlet flowing down, and there is a valley. It's passing a valley, this ice flow, and damming up damming up water. So the water is accumulated here, and until it has reached such a pressure that it is able to force its way under the glacier all the way down to the margin of the glacier, or to the front of the glacier. And then, so we have marginal lakes like that. I'm sure there are many like that in the Himalayan mountains. I just want to point out to you, since I was talking about the subglacial lakes, show you just one picture of a lake like that, where you have a depression in the surface and the lake underneath. And that was this one. This is from Iceland, and this is a circular cauldron, a depression like that in the surface. There is another one there and the third one there. And as I told you, the pressure all around at the base of the glacier is higher than it is underneath, and therefore water is accumulated, moving into the center here under the glacier and forming a lake or a water body which is rising up above the bed. And this is the type of subglacial lakes we have in Iceland, and the reason for this is that, as I said, that we have geothermal heat melting continuously ice in this spot under here, and therefore a depression is created in the glacier surface, and this leads to accumulation or formation of lakes underneath the glacier. We can also have, as you see here in this type of lake, which is supraglacial, or it's on the surface of the glacier, and they are now becoming more and more reported lakes like that, and they look like this. This is from Greenland. So lakes are forming on the surface of glaciers. And this is a consequence of increased melting in Greenland, that meltwater is produced on the surface. It is a cold glacier, so the meltwater, well, it penetrates a little bit into the glacier, into the snow, but there is more melt than can be removed by penetration. So water is accumulated on the surface, and there are many lakes like that, and this is new, and as I said, because of increased melting on the, and then they are suddenly drained. So this is a cross-section from a recent publication. There was a recent publication in Nature about this only a few weeks ago, or maybe 2-3 weeks ago only. And here you see the lake, and they were exploring how they were drained. Suddenly water is flowing down from the lake towards the bed and out in a flood. And what is more important is that you suddenly get water down to the base of the glacier, increasing the lubrication by water at the bed and rapidly increasing the sliding, and the glacier is rushing forward during the drainage of lakes like that. And this is increasing the ice transport towards the coast of Greenland, and this is very much debated now in glaciology. And I can tell you that nothing like that is included in the models of the IPCC, where glaciologists have been providing models of glacier flow, and I will talk about that in the last lecture. But there is a very severe lack of knowledge about what is really going on in the flow of the glaciers during warming or during increased production of meltwater. So this is a very hot topic now in glaciology, and there was nothing about this in the IPCC report in 2007, and when you look at the last one from 2013, the situation is the same. The glaciologists have not been. There's more discussion about this, and it's not in the model yet. So there is an intensive international work now on understanding more about these surface lakes. And then we have the last type of lakes, which is proglacial. It's in front of the ice. Here you have the glacier, and you have a moraine in front of it, and the lake is formed here. And this is the typical type of lakes which are now at an increasing rate produced in the Himalayas mountains and many of the mountain, in front of many of the mountain glaciers in the world. And this is a sketch of this. So what you, now when the glaciers are retreating, a lake appears in front of the glacier. The glacier continues to retreat and the lake becomes larger and so on. And then in addition to this, so this is a moraine, and there is a depression behind the moraine because the glacier has been eroding its bed and pushing up a moraine in front of it. So this is obviously a good place for water to accumulate. And well, in most cases there is a river cutting through the moraine and everything is okay. It's just raining into the lowland in the rivers. But if no river is draining from these lakes, then there are problems, because then water would accumulate until you get an outburst. There's also one point to mention here, that when the glacier is removed from this land, a lithostatic uplift can take place, because the glacier has been pushing down the ground, and when it's removed, the ground or the crust is able to lift up. So that is an additional component here, which might form a barrier. You may have a moraine, as I said, but you may also help by lifting the ground which has been depressed by the glacier before. So this is another one, and I just took this by looking into Wikipedia or something like that. This is a glacier, this is a glacier lake, this is a moraine. So this is so the problem whether a lake like that will burst or might burst is not a problem of glaciology. It's more geotechnic. What is going on here in the moraine? That is the problem. But it is a very serious problem in many parts. Here you can see a proglacial lake. This one is the glacier is there. It's been pushing a big moraine here, and now it's retreating, and a lake is formed here in front of it. Fortunately, there is a river, or maybe it's man-made, just by cutting through the moraine and helping the water to escape continuously. But, so this is in Wyoming, in the States. There are other, I just picked out some images about this. This is one, a very, very steep glacier. It's somewhere in the Himalayas, and a lake is in front of it. And it can be dangerous. The glacier once, you can see the mark or the line here that the glacier was in earlier days covering all this, and now there is only a lake left in this region. Here is some remote sensing data from Bhutan, and they can observe that this is an outlet glacier, and there is a lake which recently has been formed in front of it. Fortunately, a river is draining this lake, so that's good. Here is another one, recently formed, and so far there is a small river also, so that's good. But So what they are doing is to scanning all over the Himalayas to find out where lakes are formed and whether they are draining continuously the meltwater or not. And, and the question is then what can be done about it? If it is not draining, is it possible to cut an artificial tunnel out? And that is not so easy at 5,000 to 6,000 meters elevation. So this is, and alternatively, it's a possibility to put up a warning system that you are observing what is, and when you see the drainage is starting, then you give warnings. This is from Nepal, and there are many, many outlets here. This is the accumulation area, obviously. There's an ablation area here. It's darker. And then the problem is to spot some lakes. Here is one, it's for sure one. And so this is a very important work for glaciologists. Now, if we now go back to, now we have talked about all the types of the various lakes. Now I will just go back to a subglacial lake. Yesterday I mentioned that the water is driven by a gradient in a potential, which is just the potential energy and the pressure on top of the water, wherever it is. And so you can, if you have data of the bedrock topography of a glacier, then you, by radio echo soundings or anything, so if you know the bedrock topography, you know this term. If you know the thickness of the glacier, you can estimate this. This is just an estimate, but it's a good start anyway. So this is the thickness of the glacier. So you can calculate this, and you can calculate the potential field, and from that you can ask, well, you can delineate the drainage basins. Well, you do that all the time from topographical maps outside. You just take the contours. And you delineate the drainage basins or the water divides. You delineate the water divides, and so in that case, we are just talking about a potential which is only produced or created by the gravitational potential, because this term would be 1 atmosphere in that case outside the glacier. But now we have to add this one, which is the pressure, which is variable under the glacier because the ice thickness is variable. And then, but it's just similar. You make a map of the potential, and you start to draw the water divides on that map. And here we have done that. This is the water divide, and all the water created or produced inside this region is draining down to this river. And here we have another one. It's draining down to there, and so on. But if you look carefully into this, you can see that there is an area here in the center of this ice cap, which is the largest one in Iceland, with no connection to the margins of the glacier. So here, so it's a closed basin, so water produced by melting in this region will not flow away. It will be staying within this region. So here we have a subglacial lake. Here we have another one, and the third one. So we can explain all the cases of lakes just from a gradient. We're looking at this potential and say that the lakes are where the gradient is zero, or is the water divides to where the gradient is zero, and that would enclose an area with lakes, which lakes are formed. And I can, I'm just showing the conclusion here that the slope or the gradient in the bedrock topography in a lake like that would be where you have a lake, which would be this at the bed of the ice, would have an opposite slope and 10 times larger than the surface gradient. So if you look at this, we have a certain surface gradient in this direction here, and I'm telling you that the water body at the base will be sloping in an opposite direction, which is here, upslope here, and the slope will be 10 times the surface slope. So you can see this is a much steeper slope here than in the depression. If you look at the the water body which is located in the depression, then the surface in this case would be a concave surface. And the slope would be like that, outside from a center here on the surface. And the bed slope would be opposite and 10 times deeper. So we would expect a water body under a surface like that only to be located or found in a deep depression like that. And here, if we look at the marginal lakes, the surface of the glacier is sloping here towards the lake surface, and you would expect the glacier to have the boundary between water and ice here to be sloping at 10 times faster and in an opposite direction. So this is the influence of the ice on the location of the water body. But here, of course, outside you have a moraine, and we are not talking about that and that's another matter. And also here in the supraglacial lakes, you have depressions in the surface, and well, that's enough to keep water here. So, well, you may wonder what this is. This is just a special case of number C here is a special case of this, where ice is still it's water, but it's the same physics behind all of this. And now I'm going to tell you about some of the theory behind this. In the beginning, people started, and this is not so old, this is only half a century old, all this theory and knowledge about this. So it's people were considering or colleagues of us then. Ice like that, that's a problem. There is water here, and the water is accumulated in this lake. This is a marginal lake. It will be rising higher and higher, and when will it be high enough to be able to force its way under the glacier all the way here and out to the snout or the margin of the glacier? An obvious suggestion was to say that the water level would rise up to 9/10 of the ice, or the thickness of the ice dam. This is, and here we are also talking about ice-dammed lakes. They are dammed by ice. You can also say moraine-dammed lakes, ice-dammed lakes. So, yes, I forgot to mention that. But anyway, that is what we are dealing with. There's an ice dam. This is the thickness of the ice here is damming up the water, so it's accumulated here. That was the first idea, that this might. And then the next question was, what would happen to the water if it started to drain down here? Then the lake level would be falling, and wouldn't the ice dam just close the tunnels? And why didn't it do it? The observations indicated or showed that when the water drainage had started, nothing would stop it. It would just go on, even though the lake level had fallen. And then the first suggestion was by a Norwegian, Olav Liestel, that frictional heat would be produced in the water, and that would melt the surrounding ice and help to keep it open. But many, many years later, the first Canadian, Bill Matthews, did a simple theoretical calculation. And he came to the conclusion that enough frictional heat would be produced to do the job of keeping it open. Then it's first in 1976 that the English physicist John Nye, who was in Bristol and still alive, he considered the problem and produced a simple calculation, because all this starts with a simple calculation. He considered a tunnel, which was a straight line here from the lake down to the terminus of the glacier. He assumed that the lake temperature here was at the melting point. Further on, he considered a model where the frictional heat produced at any place would be used instantaneously to melt. And you just assume that the potential heat is producing frictional heat, or used up in that as the water is flowing. Of course, it was a question whether the water might become warmer and warmer because they couldn't get rid of the frictional heat, get rid of it by melting. But this was his assumption. And then he considered a simple model where he neglected the closure rate of the overburden ice, because you have a tunnel here, and it will be growing in size because of friction will melt the ice surrounding ice. But then you have a thick glacier on top of it, and that might would obviously try to squeeze this together. So you have a tunnel which is can expand due to frictional heat, but it will be compressed by deformation of the glacier ice. But he looked at the simplified problem of no closure. So he came up with a very elegant suggestion for the discharge rate in a tunnel like that. It would increase rapidly with time, which is T, and approach, well, this would be an asymptotic approach to a straight line here at the time T equals 0. And then, so it's rising more rapidly than exponentially. It's rising like that. And of course it wouldn't rise to infinity because there is no water to do it. So this was a success because it turns out to look very much like hydrographs. I will just jump to this. There are many hydrographs measured, and here from Iceland we had collected many hydrographs, and they were rising like this. And here is one, another, and so on. So he was able to simulate something which looked like the observations. He did a complete theory of this. So he considered the entire problem, and I can tell you about that. So the entire problem is that you are looking at a tunnel under the ice. Water is flowing through that at a discharge Q and through a cross-section of an area S. There is some temperature of this water. It might be at the melting point, but it might also be a little bit warmer. And so it has a water temperature. And it has a water pressure inside this tunnel. And then outside the tunnel, you have ice. And this ice has its own pressure, which is here in this, given by the height of the overburdened ice at that place. So it's assumed to be, glaciostatic or hydrostatic or whatever you want to say, how you would. But anyway, it's given by this. And then there are 1, 2, 3, 4, 5 equations which have to be formulated to solve the problem. They are partial differential equations. First, an equation for the geometry and flow of ice. So the change in the cross-sectional area will be given or determined by the melting of the ice, because when you melt the ice, you are changing the cross-section. And then there is an ice overburden pressure trying to squeeze this tunnel together. And you can recognize here that we are talking about the difference of ice pressure and water pressure in a power of n. So this has to do with the Glen's law, which I was talking about 2 days ago. So that you recognize this. Then you have continuity. You have to do where the cross-sectional area is expanded with time due to the melting, and it's also due to influx of water through the tunnel. So this is just input-output, as we also mentioned sometime. Then next you have to go over to the relationship between discharge and the energy flux forcing the and the gradient in the potential. This is the same potential as we have talked about over the distance, is doing the job of forcing this amount of water through this, and it's in a tunnel which is well, has friction and roughness and so on, and this is the equation for that. Sometimes if you're a hydrologist, you may have heard about the Manning equation. So it's often used as Manning, and the gradient in the energy doing this is then given like that. But then we are into some thermodynamics, that you are producing frictional heat in this, and you may be changing the temperature also with time, and it's depending on pressure. And here we have to deal with, or include or think about how the melting point of ice or water, freezing point, is depending on the pressure of the water. Remember the phase diagram for water. And so this is okay. So this is the total melting. So this energy here goes into melting and maybe heating of the water. And then in the end, it is the question about the heat transfer. You're producing some heat inside this current of water, and how fast can you move it to the walls of the ice tunnel to do the melting. And then we come to this. This is an empirical equation. So it's telling you that the melting you are getting there, and which is this one, and the change in temperature in the water you are producing, is given by a rather ugly empirical equation, well, depending on this is an engineering equation. This is Q. You can recognize Q here, and the viscosity is here also of this material, and you have and this was developed for by engineers for types, flow of types, or tubes. I mean tubes, and it turns out that this is not a good equation. It's still an unsolved problem how the heat transfer is. You may also add, if you have a lake, and you can add a continuity equation for the lake. The change in the lake would be what is going in and out, and yes, and the main glaciologists of Rattlesberger and I, Gary Clark and Houghton Springer, did this theory which is outlined there. Now, if we go to observations, so people were very happy about all this theory. It could explain a lot. Here is a record of changes in lake level in this lake, which is called Grímsvötn in Iceland. And the lake was rising up to a certain limit, always just about the same, and then started the flood, and the water was draining 50 kilometers down here and even 200 meters below sea level and up again. And we collected a lot of data on this. And And they gave results like this, very nicely increasing with time, and it was obvious that big floods were rising faster than small ones, and this could be explained by theory. But then came one what happened now? But then suddenly one Jökulhlaup started, which could not be explained by the theory, or this theory. And that is here, 96 and also 1938. They were rising much faster than could be explained by expansion due to frictional melting in the ice tunnel. So it was obvious that we had two types of Jökulhlaups. One, which could be explained by the old theory, or classical theory, rising slowly up from a peak, and another one, which was rising very, very rapidly and declining slowly. And here you have examples of that. This is discharge, and this is a lot of water, 40,000 cubic meters per second, which is a lot. And we know of floods which are much larger than that, but anyway, this is. And when looking into this, the melting of tunnels cannot make space for water at this rate. It was just impossible. So what happened? What can explain that? And what happened was simply, well, this is just a flood like that, that there was no time to make a tunnel like that and let it expand like that. What happened was that the glacier was just lifted from the bed, and the water was flowing over a sheet, a large sheet. And that was the conclusion of these observations. So sometimes a tunnel is doing the transport, but in other cases it's much faster flow and can only be explained by the water lifting the glacier and spreading along the base. And here are some results of the or an attempt to prove the model. It's by Flowers. She's a Canadian colleague, and others. And so, and the paper is, well, let's first look at the observation. We are out of the lake. This is the hydrograph of the water coming down like that. The drainage out of the glacier margin started later, 10 hours later, but then it came with full speed, and the peak of the flow out of the glacier, which was 50 kilometers down glacier, reached up to 50,000 or more, 50, 60,000 cubic meters per second. And then it fell rapidly down. And this has been modeled as a combination of two types of flow. The water is, first spreading all over the bed. It's not contained in a single tunnel, as in the classical theory. This is conduit. But it's spread out. And then, so there is a seed flow in the beginning, going up like that. And yes. So, well, you have to look at that yourself. There are two hydrographs here, one for the seed flow component and another one for a conduit. And what happened was that the water, or we suggest that the water was spread out over here and then collected later into a tunnel. And in this case, water is added to the tunnel everywhere. Whereas in the classical theory, water is coming from a lake and into one end of the tube and out of the other one. But in the classical, in this model here, water is able to flow into the tunnel along the entire glacier bed. And this is a much faster way of transporting water down into a conduit or tunnel than doing it just from the end. So what we have here is not a tunnel system entirely, as we talked about yesterday, which is really fast, of course. But we start with a distributed system, which is slow in nature. But then the distributed system is developing into a rapid tunnel system. So this is the result, and this is published in Geophysical Research Letters. There's some more here. Unchanneled nature of initial outburst, turbulent seed flood arrives first that broke into conduits. Okay. So it's a seed which is then broken up into tunnels very fast, transporting the water. So this is the situation in this topic of glaciology. Typically, we have very fast flow and no problem with the water. It can be accumulated under the glacier on the surface, and then I have explained the theory about that, at least marginal lakes and subglacial lakes, but how supraglacial lakes are drained is something glaciologists are working on, and there was a paper in Nature on that, so it's a very, very new topic to understand that. And then the question is, and the main problem for you here in this part of the world is, however, what is how a lake like that might drain, and that is indeed not, well, it's a problem in glaciology, but not only a glaciological problem, it's more a geodetic problem. But so that is something new. And the question is, what about the discharge rate? Do we know something about the discharge of floods like that? Yes, we do, and they are very, very fast. When a moraine is breaking, it's just crazy. I mean, the water flow is more like this, very, very rapid rise, and so it's a dam breaking problem. If you well, and dam breaking problems are very much studied by civil engineers. What happens if a dam is breaking, a reservoir is releasing water instantaneously, and that is a flash flood. It's very, very fast. And but I am not talking about that. I'm just pointing out that you have to look into some civil engineering textbooks about dam breaking if you are going to work on that. But this was my talk today. So, and then we have practicals at 2 o'clock. Okay, so see you at 2 o'clock. Yes. Possible.
One type of glacier lake can get transformed into another, like some glacier lake can convert into marginal to convert into glacier lake.
Yes, that's a possibility. Yes, that if the glacier is retreating and opening up for yes, a marginal lake could be a proglacial lake later on in time, and then you could have you can also have depressions in the bedrock surface and new and development of new proglacial lakes. So the only way is to look at the satellites but that shouldn't be difficult to detect proglacial lakes. The problem is whether you can do anything about it if it is not draining continuously but accumulating water. That would be your problem. Well, it's I wouldn't expect much subglacial lakes here in the Himalayas. You may have some water pockets draining out, but it's not a large lake under the glacier in this case. We have them in Antarctica and under large ice sheets, but they are not large under valley glaciers. But you may have some supraglacial lakes. You just have to look, and they can drain as you. Yes, and then down to the base and increase the lubrication and cause some problems with the glacier, increased flow of the glacier, and so you are facing it's a tricky problem here in the Himalayas, but I thought it was useful for you to know. The problem in general, yes, I sent a letter to Norway and I got a reply, and they're looking into this. Okay, so well, I will before I leave, I will send another email to them. So, okay. Oh.
Good morning once again. Today I am going to talk about this errors and accuracies. In fact, the two are very closely related. And sometimes the notion is that moment you say error, we tend to hide it, saying that something, we have made a mistake. But the fact is, it is an integral part of the observations, and you have to be aware of what that is. Okay, there's nothing to be afraid of, but you should be aware of. In science, all the theories, most of the theories, they depend on the information you have. Okay, you are all familiar with astrophysics, right? They look at the stars and there are the telescope. Typically, if you look at their life, it starts after sunset. Okay? And professor and student go to the observatory. Professor relaxes in the room. Students goes, takes observations, comes back and reports, and then they start discussing. So there is a story about this that is a very famous professor. Student was reporting every 2 hours what he observed. At 12 at night, he came and said, "Sir, I observed this, this, this." Then professor thought for a few minutes and then gave a beautiful explanation, theoretically why it should be so. Okay. Then at 4 o'clock in the morning, a student comes back and says, "Sir, what I said earlier was wrong. This is what the correct thing is." Again, professor closed his eyes, thought for a few minutes and gave another beautiful explanation why his observation is correct. We have an explanation for whatever you observe. Okay. The question is the observation correct? That's what matters. And what is the assumptions or uncertainties in the observations that limits your conclusions? That is something one has to be aware of. In fact, this is one of the latest paper on global warming, which appeared in Science in this month's issue. Possible artifacts of data biases in the recent global surface warming. Okay. Again, it comes back to the question of what we are analyzing, how we are analyzing, and what we are concluding. Okay. The main point in this paper is that when you look at the history of all this global warming or what you do, the data that goes into these different time periods are different. Okay. In the process, you are likely to make errors because sometimes observation in a particular location is not available. Then you add to that. Once that is added, it changes the dimension of the problem. And therefore, some of the conclusions, one has to be aware, like what is the actual data used in this conclusion or study. Normally, these observations are the ground truth, right? That's what you take. Like if you have a theory or a model, you want to test or compare with observations, but what is the meaning of this ground truth? And that's where the uncertainty issue lies or error issue lies. Like for example, if you look at, this is one of the popular curves, right? When you discuss climate, you talk about how the climate was, say, 100 years back and how it is changing rapidly now. And these are all scientific analysis, and each one of them, they correspond to the analysis by some group. Okay. And you see there are differences. Each difference depends on what they actually used in their study. There is broad agreement, but there are finer differences. Like for example, one shows this much, another shows this, other shows this. See a lot of difference. Why they differ so much? Because it depends on what data has been used. And all of you are familiar with this issue of global warming. You go back to 1,000 years, how cold it was, then 1,500 years, how it was, and now how it is. So this was the source of data to look at paleoclimate 1,000 years back. Okay, you see where they are located. All in the northern hemisphere, again, mostly in Americas and Europe and partly in Africa. When it comes to 1500, again, these are all paleoclimate data, more number of studies, and then these are included. So when it comes to 1750, the coverage is better. What about this? Hardly any data from the southern hemisphere. Okay, so there is a strong bias in the entire climate data set. Often what is hidden is this information. When you see those curves like what I showed there, okay, we always like to see some nice variation, okay, someone interpreting beautifully. But what is ignored is actually what is the data used in the study, how it has changed, method of analysis has changed, proxy has changed, and how that has contributed to the conclusions that they are drawing. In fact, this is the global warming trend. There was this thing in the latest IPCC report saying that it looks, this red line is the old corrections is reported in that latest IPCC report, saying that almost there is a halt in the global warming signal. But if you do this same data, analyze it slightly differently, it turns out that global hiatus is not there actually. Still, the globe is warming. Okay. So if you are interested, you can go through this paper. This is Carl et al. Science, the June 2015 paper. Okay, it gives an idea of how, when you analyze differently or look at the data more closely, you come to a different conclusions altogether. Okay. And we are all familiar with all India monsoon rainfall, right? Because every March or April onwards it starts Indian summer monsoon first forecast, later on end of the season what the actual value is, then you look at how the variation is in the last. It starts with 1875, comes all the way up to about 2015 now. And you see this is the amount of, is called Indian summer monsoon rainfall. That is the rainfall that fell over India over a period of 122 days, 1st of June to 30th of September. It includes 122 days. If you add up in a way like weighted average, then this is what one stick is the result of the seasonal rainfall. You have to wait, and that is what this number is. It summarizes overall what is happening over India. Okay, this is the average, and there is a variation about that. Okay, and this is the normalized departure from this. Okay, looks very nice. But when you look at where the observations came from in creating that rainfall data set, if you see where they are all located, there is a big density of network in south. Maharashtra and Gujarat is okay, but if you see, this is one of the main monsoon zones. Okay, Bihar, Jharkhand, and part of UP, hardly any data. Okay, in fact, therefore, but when we present this information, we get the impression as if entire India is covered, and we are get this is one number which represents what is happening over India, but spatial representativeness is very poor. Okay, in that whatever you see, and often what is not given importance is this, saying that hardly any coverage in part of the India where it rains heavily. Okay, so therefore, if you change the rain gauges here, add few more, your entire rain climatology will change. Okay, what you include and what you exclude. And in fact, if you do district-wise or 1 degree by 1 degree, how many rain gauges are there in the country? If you look at in south, you have 20, 29, almost 30 in some places like that. But if you look at here, not a single rain gauge or entire 1 degree by 1 degree. Okay. So what do we do when data is not there? Interpolate. Okay. So therefore, many times what you see beautiful curves, they are result of interpolations or extrapolations sometimes, but it may not be the actual truth. I will show you one example where this is the status, I think, about a few years back when that IMD data set was created by Rajivan et al. Okay. So this gives you that distribution of the rain gauges, where it comes. All right. And more disturbing factor is this, that if you go back to 1950 or up to about here 1990, you used to have more than 1,000 rain gauges. But if you look at the last 1 decade or so, the number of actual reporting stations, that is coming down. That's another thing that one has to be concerned about. So it is not strictly that this one. So because of this, when you look at these different data products, like for example, one of the very popularly used this thing is IMD gridded rainfall. Similarly, you have this GPCP, right? That is also used very popularly to compare with models, for example. There are big differences between these two. Okay? depending on what is included, what is excluded, how many gauges are there, all makes a difference. So therefore, the question is, what is truth now? Is GPCP the correct or IMT is correct? When you compare the model, how do you calculate the error? Okay. Always you would like to say 10% error, 15% or this one. When you look at here, among two ground truths themselves, there's a big difference. Okay. So therefore, observations have uncertainties. So when you make this use of this data, be aware. So try to go a little back in further, more into details of how this data is collected, what it means, can I trust it, and what are the limitations. Basically, many times the problem comes because people are not aware of what is the limitation of a given data set. Okay? If you are aware of it, then you know this is uncertainty. I can't go beyond and conclude more than what is there in the data itself. But that often people ignore and they conclude more than what is there in the data. This is a classical example of what we understand based on what is available. Okay, let me explain what it is. It is the temperature, sea surface temperature reported from the North Bay of Bengal. The year is 1998, period is June to October, and what is plotted is SST, 28 to 31. There are two data sets. One is Reynolds, it is a weekly or what you call pentad, means you have one data point every 5 days. So that is this one, green one. Okay. And till 1997, we didn't have other source of data at all over the Bay of Bengal. Then this national NIOT, Chennai, they installed a buoy here. And what is shown in the red line is the data, SST measured by the buoy at this location where same SST is reported. And you see, this is the variation which is reported by the buoy. On the other hand, if you look at the Reynolds SST, that shows a trend like this. Now, if I were to explain what is happening over the bay based on this green line, it looks like pre-monsoon, the SST is high. Remember, this is June, monsoon onset is there, so SST cools by about 1 to 1.5 degrees, and then rest of the season, there is a gradual cooling, okay, by about half a degree. So this gives the impression as if ocean is a big reservoir of heat. Atmosphere just extracts that heat, and because of that, the cooling is occurring. Okay, the ocean becomes a passive supplier of heat or energy to the atmosphere, hardly any role to play at all. But on the other hand, if you see the other curve now here, what is happening here is ocean cools below 29, it goes above 30, 30.5, again cools down, and you see very strong intraseasonal oscillation here. So here, ocean becomes a very active participant in the monsoon dynamics. Okay, here there is a strong coupling between the atmosphere and the ocean. Here the coupling is hardly anything. It's just a passive background or surface which just keeps on supplying the energy needed by the atmosphere. So therefore, the kind of theory you will be doing, assuming this and assuming that, are completely different. Okay, so it all depends on what data you have. Okay, you can always come to any conclusion. That's possible, but the question is, truth could be very different unless you have the actual data or the correct data could be leading to wrong conclusions. This I'll show you one example of the effect of interpolation. One of the satellites that I admire a lot is TRMM. Amazing. It was launched in '97, was supposed to last initially for 3 years, then 5 years, but eventually lasted for 15 years. Okay, and the kind of data it has is amazing. So if you plot buoy SST along this x-axis and the TMI SST, it has a SST sensor along this axis. At these two locations, we have buoys, and this is co-located and simultaneous. That's what you have to do. And you see the trend. There, one is north. This is red is north. This green is south. All of them they lie along this one. And this is the uncertainty. If you look at this, is about 0.5 degrees centigrade. But in the mean, if you look at, the difference is about 0.1 degree centigrade. So from space at 400 kilometers. On a monthly time scale, you are able to measure SST to an accuracy of, say, 0.5 degree centigrade, 0.1 degree centigrade. Is a remarkable scientific achievement. Okay. Now, this looks beautiful, but if you go go a little more detail into that, then what do we see? This is the temperature. Red is the one which is reported by the TMI, that is the TRIM satellite, and green is measured by the buoy, and this is weekly average, okay, 7-day running average. So what you see here is that in the mean both are able to follow beautifully, but the problem lies in the amplitude of what you call as the intraseasonal oscillation. There are periods at which you see this is the actual buoy temperature, but this is what is reported by the satellite. Okay, it is reporting, if you see this scale, this is about 1 degree centigrade. There is a difference of 1 degree centigrade between the two temperatures. TMI or a satellite is saying it is 1 degree cooler, but the actual observation is that it is more than that. Okay. Now, for example, if I have to develop a theory to go from here to here, essentially when you look at cooling, you have to remove the heat somehow from that particular layer of the ocean. Then how do you remove the heat? You have to either evaporate or mix more cold water from below, one of the two. Okay. So therefore, you have to think of way how to remove the heat, but then over a very rapidly it starts warming also. You have to supply heat. How do you supply heat? Only way of supplying heat is solar radiation. Okay. Otherwise, there is no other heat source. So there, or you have to add some advection saying that okay, up to this there is one water, some warmer water came and occupied there, or some other theory you have to do. Okay. So therefore, again, this is another example where what you have or what you conclude depends on what you have or what you observe. Okay. Now, why that problem arises? So we had a cruise in the year 1999 in the same location where I showed in both the places we had ship observations, and what is plotted here is the temperature SST measured on board the ship, and these dots are the points which are measured by the satellite. Okay. And ship was there for about 20 days, came back on supplies and went back again, same location. Therefore, this is the data missing. And when you actually look at what's happening here, like here again, there is a difference of 1 degree centigrade. Okay. Whenever you have this cold bias, what you call, it so happens that these are the periods with clouding, but TMI has an algorithm for removing clouds, but there is a threshold. If in the borderline of that threshold, it recognizes it as a OK SST, but actually cloud is sufficient that it is actually altering the SST. That is one. And also these are the periods when the wind speeds were very high, like you can see here, wind speed, more than 10 meters per second. And one of the assumptions made in deriving this SST is regarding the emissivity of the ocean surface. You assume that it is 0.99 or something. But as wind speed increases, what happens is that air bubbles are trapped at the top surface. You see a large number of these white caps. Okay. As a result, emissivity doesn't remain at 0.99, but actually decreases. Like for example, it can become 0.97. So the original assumption that assuming 0.99, you derive the SST, but actual emissivity is less. As a result, you tend to underestimate the SST, because the assumption is that whatever the radiation you receive, let's say R is proportional to or equal to epsilon into sigma t to the power 4, right? If I use higher epsilon, you get because this is what is measured for a given R, then I get lower t. On the other hand, if epsilon is less, I get higher t. The problem here was that it is to do with the emissivity of the surface, because as the wind speed increases, it does. So TMI algorithm doesn't include that physics. So we reported this in that Journal of Ocean and Atmospheric Technology, and we are hoping that things will improve. But when I look at data in the year 2011, same kind of problem remains. It has not improved. Okay? People have not accounted for this effect of changing wind on the emissivity. And so this is EMSRE is nothing but this is the SST-based, satellite-based SST product. This is the actual buoy. You can see again, there are these times when buoy becomes the tier or the satellite SST becomes very cold. Okay, so the problem still persists, and the difficulty is that people do theory based on this green line, and they come to a lot of very strong RC coupling. But the fact is, RC coupling is much weaker than what is expected from this data. Okay, that's what happens. So basically, we use a variety of instruments. Okay, yes. See, yeah. See, Argo floats, the problem is that they give up to about 5 meters or so. Okay, as top surface they don't give. The other problem is their temporal this one sampling. Every 2 weeks, one profile. Okay. And still you don't get SST. What you get is mixed layer temperature to some extent. Okay. But if you want to, if you are looking at ocean profiles, yes, Argo floats are making a lot of difference. So, in fact, when you look at all the instruments from which we took the data, all of them, they follow certain rules or guidelines. Okay? There's something called accuracy, precision, resolution, and error or uncertainty. All these are established for them. It is people, those who actually give the instruments, they are aware of it. Instrument makers are aware of it, but often users, they ignore all this. They would like to just use the data, forget about how it is collected. Okay? Now, what is accuracy? Accuracy is the closeness with which a measured value is to the true or an expected standard value. Okay. So therefore, essentially it is a degree of agreement between what is the true value and what is actually measured. Okay. Then it is purely a relative term. Okay. The reason is that many times this true or the standard values are defined by us. Okay. Like for example, when you look at temperature. Okay. On a degree scale, freezing point of water is 0 degrees centigrade. But on Fahrenheit, that 0 is something else. Okay. Just think about what does the 0 correspond to in the Fahrenheit scale, and why you got 32 as Fahrenheit as 0 degree centigrade or freezing point of water. Just try to figure out why you do that. So therefore, many of these things depends on how we define a particular physical quantity. So this error is every measurement technique has limitations. That is one thing you have to be aware of. Okay? Every technique has limitations. One has to be aware of it. And error in a scientific measurement usually does not mean a mistake or a blunder. You know, many times we associate error with a blunder. Okay, it is not that. Okay, error means it is part of the measurement process. Only thing you have to put a bound that. Okay, what that limitation is. So the term error and uncertainty both refer to the unavoidable imprecision in measurements. Remember, unavoidable, that is the term there. Okay, what is the meaning of this unavoidable? Okay, many times people think, why can't I make it? Why is there a problem there? Okay, let me give you a simple task, and then you realize what this unavoidable means. Okay. Okay, very simple problem. Let's say I want to measure the period of this pendulum, period of oscillation of this pendulum. If I had sufficient time, I would have given one small chit to all of you, ask you to measure and report that time is. When you put those numbers on the board, then you realize how spread it is. It is not, some of them are not very close at all. In fact, the differences between them are quite large. Okay? Why that problem arises? You can think about it now. First problem arises, like when do you identify that it has reached that other end? Okay, that's the starting point. Next time you have to say, oh, now it has reached the other end, I have to stop. Okay, so that involves your physical response and then pressing that. So it is a this thing. Like for example, persons like Sachin Tendulkar or De Villiers, they have such fast responses, they can do tuck immediately. But most of us, we don't have that kind of reflexes. So there is a time lag between what we actually observe there and acting into our hand. And then that goes to that instrument, and then we stop the clock. Okay? So therefore, this is the kind of uncertainty. Means I can't go beyond a certain limit. Okay? Every time there is small fraction of time where it is uncertain, like when I treat it as it has reached. After seeing that only I press. So when you see the differences, they are also related to person variation in this response time also. Okay, that is why you see this. This is what I mean by unavoidable. Okay, so many times it arises. Another one is this. That basically what is done here is that a certain number of molecules are released. Okay, only problem is that they are moving randomly. So therefore, the number counting, remember, 1, 2, 3, 4, 5 is a very definite. There is no uncertainty at all. You can, if you know the number, you can always count, and then uncertainty is 0 actually, ideally. But problems like this, you know that the number is bounded. There is only fixed number of particles are there. But still, when you try to count, even if you take one instant in a freeze and do it, what happens is few molecules may be behind the other. Okay. Next time you count, they will come out. So depending on how much their overlap is there, again you find that each, suppose you repeat this measurement 100 times, each time the value is slightly different. But when you average them, there is a mean and also standard deviation. Okay. That is what this unavoidable imprecision means. Okay. So this is what it gives you a feel for what this unavoidable imprecision means. Means moment you look at that particular measurement process, okay, there is a limit up to which you can be certain. Beyond that, your uncertainty band is there. Okay, that's what matters. So this is where the precision is the closeness with which individual measurements are distributed about their mean value. Okay, so basically, precision is a measure of the degree of agreement among individual measured values when repeated under same conditions. You know, many times, you know, this is understood, okay, but basically you have to keep all other conditions same and then repeat the experiment and see. Basically, a very precise instrument need not be more accurate, okay. One of the standard example given is this dart, okay. Like for example, this is what you want your darts to be hit. That's where, suppose you throw a dart and suppose the person is doing that, okay. Then you see all the 5 of them, they landed here, but ideally they should have landed here. This is the aim, but this is where they ended. But there is a consistency here that all of them are close to each other. So we call this as accuracy low because it is away from the target, but precision is high because the agreement between individual attempts is very high. Okay. On the other hand, in this case, you think it is not a good example, right? But the fact is, in scientifically, the accuracy is high here because if you look at them, they are centered around the true target. But the precision is low because the spread among individual atoms is large. So the ideal one is what we want is this, where accuracy is high and precision is high. Okay. So if you plot along this, let's say this is your reference point, and these are the mean of the individual attempts here or here like this. That's the mean, and around that you have a spread. Okay. Now, spread of width of this curve is an indication of what the precision is, and thus this distance between reference value and the average or mean of these individual atoms is an indication of accuracy. Okay. Question is, can we reduce the error? Because everyone wants to do the measurements as accurately as possible. Okay. Question is, up to what extent can it be reduced and what is the final limit? To do that, you have to be aware of what are the different types of errors you have. Okay. Unless you know what kind of error is there, how to reduce it. Something called random error. Okay. Like for example, that molecules or atoms which are moving, that is random error because every time some are behind, some are come front. Okay, one to the next, the variation is that this is what that gives rise to the random error. Errors that can be reliably estimated by repeating the measurements are called random. Okay, you repeat the basic idea here is that some values are above the mean while some are below. So that's why we call this random error. And often by error or imprecision, we mean random error. Most of the time, whenever we say the error, it is a random error, And the assumption here is that if you repeat the same measurement under the same condition a large number of times, the uncertainty can be reduced. One classic example is, in astrophysics, if you attend any of these talks, they report to a temperature of 0.00001 Kelvin accuracy, plus or minus that. But we all know that the uncertainty of individual measurements is of the order of 0.01 or 0.001. You don't go beyond that. Okay. How do you come to that fourth or fifth or sixth decimal accuracy? The advantage there is that if you look at the space, the background is so stable that you can repeat the same measurement billions of times and take the average of that, and that reduces the uncertainty by that kind of limit. Okay. So it is basically related to your averaging when you repeat it under same conditions and the assumption that your source temperature has not changed. This I have shown you. So whenever you report a value, you report a mean plus or minus the standard deviation. Okay. So this gives an error of the uncertainty, what is involved, and this is the mean. Okay. That's what. One is what I said is random, which is inherent part. There are also some other sources, okay, which are not truly random, but it's associated with how you set up a particular measurement. Like for example, interference error. Okay. So if you have looked at the signal which comes from a thermocouple or one of the devices I showed yesterday on an oscilloscope, you may be amazed to find that it no longer is a smooth curve, but in fact there are large number of oscillations are there, very highly fluctuating, but the amplitude depends on whether you are close to power, high voltage power transmission line or away from it, or any source of some strong electrical signal like motor or something there. Okay. So this interference error basically comes from this, the source of some induced voltage nearby. Okay. So to the extent possible, you try to avoid making or putting your instrument in a location where the possibility of interference, or you have to be aware that what is the problem there and try to filter out that data. So that's the interference error, it can be avoided. The next one is installation error or application error. Okay. This is something which takes little time to appreciate what that means. Is that if you look at, yesterday I showed you that WMO has recommended how to make observations. What is the reason they have such a big guidebook? Actually, when you download that particular handbook, it has more than 300 pages. So first reaction is, oh, so big, I don't want to read now, I'll read later. Okay, that's what happens. But there's a lot of useful information. One of the things they have done is each observation, how it has to be taken, how the exposure should be. Okay, why they did that? Because when you look at climate data, observations are collected at different parts of the globe, across ethnic groups, languages, culture, everything. Okay, but you want certain uniformity so that some possible human and other installation errors are avoided. So they are very clear or precise in what has to be done, how it has to be taken. So one of the point there is that if you want to use your data of temperature or wind or something for climatic applications, the instrument should be mounted on a flat horizontal surface away from buildings. Any observation taken on top of a building is not a good case for or scientific data for climate studies. So from that point of view, the AWS we have at the top rooftop cannot be used for your IPCC reports purpose. Okay, even if I collect for 25 years or 50 years, again that uncertainty remains because on the top of the roof. Okay, I can use to understand what's happening over in this area, how it is changing, when the rain is coming, when the time is temperature maximum, all those things fine. But it cannot be used as a part of a long-term climate data for comparing with data from other locations. Okay. Similarly, you have urbanization now. Okay. So what happens is that earlier when that particular like IMD observatory was there, then no other building was around. But if you go to like for example Majestic, there what you find is that around IMD, large number of big multi-story buildings have come. So the exposure has completely changed. Okay. Again, So therefore, now if you move that sensor, a different location will also have its own disadvantage. So that's what happens. So many times you want these observations to be taken in ideal condition, but circumstances are such that it is not possible occasionally. But you have to be aware of what is the consequence of this. Okay, that installation error, application. Other one is human error. Okay, basically it is two ways. One is yesterday I showed you that sling hygrometer, and the recommended time is that one should be swirling for at least 2 to 3 minutes. Okay, so that there is equilibrium between the thermometer and the surrounding. But often people are not that patient. They do this for half a minute or 1 minute and take reading and go. But it has not reached that equilibrium at all. So this is what you mean by human errors. Basically, we don't pay enough attention to the instructions or what should have been done, but we don't do something else. Sometimes something else also happens, that if you are used to measuring temperature or humidity for a long time, like looking outside trees, how the leaves are moving, you know, now the wind speed is less than 2 meters per second. Then you write without actually taking the observation, okay, 2 meters per second. When it's moving little more, you make it 5 meters per second. You know, this is another kind of human error. Okay. You know, I'm not joking. It has actually, it happens. Because sometimes in the ship, no, when we go, we have to take data every 3 hours. At 3 in the morning, early morning, who wants to take? So if you go and see the logbook, at 12 itself, 3 o'clock data is already there. Because person who has been there for a week, he finds that between 12 and 3, hardly any cooling. So whatever is SST or temperature at 3, 12, you subtract 0.1, it becomes temperature at 3 o'clock. Okay, very simple extrapolation. Okay, so that's what becomes our human error. Then zero drift, it has to do with, you know, all the instruments, they have finite lifespan. They deteriorate with time, and some of the things which are not aware of is that even that standard thermometer you use, mercury in glass, there also there is a zero drift. The reason is this, that remember glass is basically a soft material. Okay, when it was formed, it was heated, it was drowned, and a hole was made, and then you fill mercury and close it. And what happens is, over a period of several years, that mercury bulb has a tendency to slightly shrink. Okay, because of that, your initial scale was using that whatever the volume was there earlier, mercury volume. But if it slightly shrinks, the entire scale gets shifted up or down. Basically shifted up. Okay, it moves up. As a result, if you put the same thermometer into say 0 degree centigrade, that ice and water bath, 10 years later, you find that 0 no longer reaches 0, but there is at 0 it shows 0.5 degrees centigrade. So even though things which look standard, I calibrated last year, thermometer don't change, some of them they do slowly change their characteristics with this one. With modern sensors, like yesterday I showed you that small piece of paper, which is humidity sensor. Moment there is a deposition of water or even some chemicals, it characteristic changes, so there is a drift in this one. So electronics changes, so one has to be aware of this. But all this can be corrected. Errors due to aging and sensitivity changes, all these are all connected with that. Okay. And additional things are there like linearity. Normally, you want the output to be proportional to input. But many instruments or sensors, they are not strictly linear. There are some non-linear variations. There is something of hysteresis. If the value increases, it follows one path. When it decreases, it follows another path. So hysteresis also adds, whenever there is a memory in the system. Moment when you say hysteresis, such sensors or instruments, they have a memory. So they follow one path while going, they come back this thing. So depending on whether it is particular observation is taken, when that particular variable is increasing or decreasing, it makes a difference. Then there is something called resolution and scale readability. Okay. What happens is that you repeatedly use an instrument, after some time the scales they wear out. Okay. And you are not pure it is 21 or 22. Okay, everything is. So you have to try to figure out what is the correct value. This is what, this also happens when you use the scale, for example, what you use for drawing the lines for a long time. Okay, it starts this one. So reading and scale readability is important. And there's something called threshold. Okay, this threshold in the sense is that the sensor's response is not there below that value. Like for example, when you look at that propeller or cup anemometer I showed yesterday, there is friction at the hub. Okay, unless the wind speed is above a certain level, it is not able to overcome the friction, so therefore it doesn't move the cup at all. So you will not get a value below the threshold. So many of such instruments which are essentially basically mechanical, there you mention or show or in fact prescribe what the threshold is. Typically this threshold value is about 0.3 meters per second for most of those cup and propeller anemometers. Then repeatability, it is also related to all these things. Basically, if you make the measurements under identical conditions, is the instrument behaving the same way or is changing its characteristics? Ideal thing is that you should have highly repeatable instrument so that given the condition, its same value is reproduced time and time within its uncertainty band. Because when you say repeatability, there's plus or minus some value there, but that should not change. That's what it means. Then span or measurement range. Okay. See, this has to do with the fact that given conditions, they demand a particular range of the value. Like for example, if you are measuring say temperature in Bangalore, I can safely say that 0 to 40 or 45 is good enough. Okay. On the other hand, if you go to Delhi, then you may have to add say -5 maximum. Beyond that, it won't go. But if you go to say Tibet, where the altitude is 5 kilometers, or in Siachen, where the temperature is so low, there again, your temperature may go outside the range of your normal instrument. So therefore, depending on what the climatology of that is, you always have to have enough buffer so that you are able to measure the extremes. Okay? That is the measurement range. Then there's something called dynamic response. It is basically to do with, every sensor has its own dynamics, the way it responds, okay, for a given input. It's like people. Like for example, if you do this experiment, hypothetical, not the real, you go and hit a person. Okay, you take some randomly people and hit. The reactions are totally different. Some will be scared and run, some will hit back. Like that, instruments also have that. Some of them, they just try to follow. Some of them, they respond, kick back. Okay. So depending on what that system does to the input, your response also changes. Okay. And what it measures also depends on that. Like standard example I gave earlier is that thermometer. When you take a thermometer and dip in say cold water, immediately it doesn't give the actual temperature. It takes some time for it to respond. The reason is it changes its temperature because there is a heat transfer from fluid into or out of the thermometer, and that is reflected as change in the height in the thermometer column. Okay? If you don't allow enough time for it to come to equilibrium, then you are actually measuring a transient problem, and there the temperature. So therefore, one has to be aware of what the dynamic response is. Okay? Then correct it appropriately. This is very actually important response. And except for this dynamic response, many of these span again is a design problem, repeatability threshold, all those things can be tested using a procedure called calibration. Okay? So basically, you estimate the accuracy by comparing with a known standard. Okay? You define the standard. Like for example, if you are say calibrating your temperature sensor, equilibrium temperature between liquid and ice, that is by definition 0 degree centigrade. So if you put your temperature sensor in ice and liquid, that is the 0 degree centigrade. That is what the calibration. Similarly, boiling temperature of water at sea level is defined as 100 degree centigrade. It is a definition. Okay? So therefore, you can take that as another standard. So you compare with some standards and this one, and use that calibration. And so, in fact, in all these measurements, calibration forms a very, very, very important component of a measurement and reporting. So most instruments, they produce outputs proportional to the variable being measured. Calibration is required for fixing this conversion constant line. Okay. Then also in the field, the performance of deteriorates and periodic calibrations are required for keeping the performance or accuracies within acceptable limits. Okay. So calibration involves operating the instruments in an environment whose conditions are accurately known. That's very important. If you don't know what the environment is, then you can't do the calibration. Okay, high hysteresis, all these things. These are all details. Okay, what I said in briefly. Okay. So, in the sense that WMO handbook, part 3, okay, it describes quality assurance and management of observation systems. Okay. In case you have doubt, in case you have to deal with analyzing the data for climatic purposes or scientific purposes, it is good to go through this section in that book. Okay. If you are dealing with data analysis and trying to arrive at some conclusions, please go through this. So then you will be able to appreciate what the information is given and what you can conclude and what you won't be able to conclude. Okay. I stop here. Any questions? Okay, I'll put the other way around. What makes you feel that monsoon is predictable? No, yeah, my question is, why do you believe that monsoon is predictable? I ask you a scientific question. That's right. How it is? No, there are a large number of studies based on that. Okay, all you have to do is read some papers which are related to the evaluation of the monsoon predictions by IMD. It has, I think there was a paper around 2002 or 3 in Current Science by Sulochana Gadgil and M. Rajivan and some co-authors, okay, on monsoon predictions, how accurate they are. Okay. It is good, this one. The problem is that most of the time, if the monsoon is normal, your prediction is good. If it is extreme, the prediction is bad. So if you put it the other way around, prediction failed because monsoon failed. Okay, but only this year the first time where IMD came out saying that it is going to be 88% plus or minus that uncertainty. But never in the past, last 140 years, they were so bold saying that monsoon is going to be deficit to the public. Okay, within the government, highest level, they might have informed, saying that you expect a bad monsoon. But in the public, never they made. The reason is that moment you say the monsoon is bad, people start hoarding. Even internationally, the prices start going up because moment they know that India, this is going to be a bad monsoon, they know what is the thing India is going to import, suddenly the price, international price goes up. Okay, just to avoid that, you take precautions or measures without bothering going in public. The moment you go into public, it has other implications. Okay. Even though IMD may be knowing that it's going to be bad monsoon, still they might like to go into public, in the public, saying that it's going to be this bad or good. Okay, that is the. But this year, let's wait and see what happens. Yes. Okay, if everyone gives the same forecast, then there is only need for one agency, right? There is no need for multiple players. Because this same thing goes back to one of the curves I showed, that when you look at some 4 or 5 different climatologies for rainfall or temperature, everything, there is large variation. Okay, it's based on what are the assumptions you make, what data sets you, what are the considerations that goes into your calculation. So they are all different. Okay, that's why. And also, in the seasonal forecast, lot of what I may call speculation or your insight goes in. Okay, I think given this condition, that is where the human input comes. Your experience matters. Any other question? Okay, then I wish you all the best. I stop here.
Everybody is, nobody working? No, it's not starting. Good morning to all of you, and next lecture will be given by Professor S.K. Satish, and he will talk on aerosols and climate. Probably many of you are aware of Professor Satish. He is one of the well-known personality in the field of aerosol studies and the related issue, and he is a professor at Center for Atmospheric and Oceanic Sciences here in Institute of Science, Bangalore. He did his BSc and MSc from University of Kerala, and then PhD while he was a research fellow at Vikram Sarabhai Space Center, and then University of Kerala, where he did his PhD. And after completion of PhD, he went as a postdoctoral fellow at Scripps Institute of Oceanography in University of California at San Diego. And he is highly accomplished professor, one of the few professors in this country who has received numerous awards. And he's quite young, and you'll be surprised to know many of his accomplishments. He has received highly prestigious Shanti Swarup Bhatnagar Award, and even though he's extremely young, he's a fellow of all Indian academies, which is in Bangalore, which is in Delhi and Allahabad. It is a rare honor for any scientist to have this fellowship in such a young age. He is the lead author of Chapter 7 of IPCC in this year, last year, which was published. And I don't know whether he keep record of his publications or not, but last count I could see is he has published around 128 papers in highly prestigious journals like Nature, Science, and Journal of Geophysical Research. And he is today, whenever it comes to the aerosol study, he is the leader of this country. And not only in India, but globally, he is one of the most sought after professor. And we are extremely fortunate to have him here. But there is another important quality of him which I like most. He is a thorough gentleman. So whenever you talk to him, and he doesn't know how to say no in life. Everybody he says this. He's a thorough gentleman, and we are very honored and pleased to have you here. And Professor Satish, please.
Thank you, sir, for the nice introduction. Good afternoon. I will be talking about aerosol and climate, and this is a 6-month, 1-semester course we are offering in this center, and the first challenge is to condense it into 1 hour. So what I understand from previous speakers and Professor Kulkarni sir is that you may not have much basic knowledge about aerosol. So my lecture will be at very basic level, and first half of my lecture I would like to concentrate on atmospheric aerosol basics, microphysical and optical properties and effect of aerosol on radiation. Mostly whatever is relevant to glaciers, only I will be talking, and please feel free to interrupt me anytime you want, and after the talk also, if you have any doubt, you are most welcome to come to my office. I am sitting in the same building. And second half of the lecture, I would like to concentrate on 2 questions. Why Indian climate science community is concerned, again on glaciers perspective. And aerosol observation, some of the observation we have made which are relevant to Himalayan glaciers. So this is the outline of my talk. And probably I don't have to introduce you about aerosol because you probably have read from newspapers. So many reports about aerosol and glaciers, everything is reported in newspapers and internet. If you simply search, you will see so many sensational news starting from, it started from beginning of 2000s. Black carbon contributes to droughts and floods in India and China, starting with that. And you will see, latest is not written here, but one of these 2011 papers say that aerosol from India stimulates intensity of tropical cyclones over the Arabian Sea. And one of this issue is impact of aerosol on glaciers. So that is another issue which you may be interested. And the whole issue started in 2003, if I remember correct. And this International Commission for Snow and Ice stated in their report at that time that glaciers in the Himalayas are receding faster than those in any other part of the world, and if the present rate continues, possibility of them disappearing by 2035 is very high. And they also focused on the impact of water supply to 1 billion people living downstream of, around the Indo-Gangetic Basin. And then at that time, it didn't get much attention. And actually what happened is later IPCC report, they have reported this, and then it got much more attention than this report. And this has become a big controversy at that time, actually. And if you search in Google now, black carbon impact on aerosol on glaciers, you will see a number of things, a significant factor in melting of Himalayan glaciers and all. Some of them are true, some of them are may not be true, maybe very premature reports, some of them in my opinion, because the knowledge about, by the end of the talk you will understand that there are so many unknowns in this field, so you can't come up with a clear answer to any of these questions. So I will, for the benefit of people who don't know much about aerosol, first a few slides I will start about what is aerosol and other details. And first half of the lecture I will concentrate on optical properties and radiative effect and all. And second half I will be talking about the aerosol actual impact from our own observation and experience. What is the effect of aerosol on glaciers? So aerosols you can define as particles of solid or liquid phase suspended in the atmosphere. So anything suspended in the atmosphere you can call it as an aerosol. And carbon dioxide is not an aerosol, it is a gas. So I already told solid or liquid phase. So it is often confused in many aspects. People think that carbon dioxide is also an aerosol because anything responsible for global warming is also aerosol. That is the thing, but it is not true. So it should be solid or liquid suspended in the atmosphere. And a typical size of aerosol is about 0.5 micrometer, making it radiatively very active in the visible wavelength region. The reason is, as you know, according to scattering theory, when the particle size is comparable to the wavelength of radiation, your scattering effect is the strongest. And I will show you some of the supporting slides also. And why it is important? The very basic question anybody can ask. Because it can affect radiation. That is a simple answer we can give. Aerosol can affect radiation, that is incoming solar radiation as well as outgoing long wave radiation from the earth. So consequences in climate, remote sensing, agriculture and health. And health issue we are not much interested, that is regional cancer centers in India are concentrated on that. And agriculture also we don't do much about it, but we are mostly involved in climate and remote sensing aspects. And you can classify aerosol into natural and man-made aerosol. Man-made is also called technically anthropogenic, and soil dust from desert region, sea salt particles from ocean, and volcanic eruption also inject large amount of aerosol in the atmosphere, and industrial emission, this is mostly sulfate particles. And finally, biomass burning and transportation, that is mostly smoke and black carbon aerosols are emitted because of this. And this is the most important aerosol species probably in climate as well as for glaciers. because you probably heard from previous lectures or newspapers that deposition of black carbon aerosol on Himalayan glaciers and its consequences. So you probably heard about that. So this is the most important aerosol species because the reason is it can absorb radiation, whether it is short wave or long wave radiation, it can absorb substantially. And if you are a physics student, you know that anything absorbed in the atmosphere will be utilized in warming the atmosphere. So that energy is utilized in warming. So whether it is glacier altitude or glacier surface or wherever black carbon is present, it is going to warm that surface. And the largest sources of black carbon are Asia and Latin America and Africa, and China and India together account for more than 50% of global black carbon emissions. So you understand the importance as far as India is concerned. And one most important thing you may want to remember here is that on a global basis, natural aerosol abundance is several factors larger than anthropogenic aerosols. But if you take the radiative effect, I will show you in few minutes how to calculate any atmospheric related things in Excel sheet or a simple calculator, because you may not want to do a complex model to calculate, make a simple calculation. So I will tell you how to convert aerosol parameter into radiative effects in case you want to use it in your glacier studies. So you will find that even though it is black carbon is only constituting 8%, when you convert it into optical properties, it is going to be about 20 to 25%. And when you convert it into effect of radiation, we technically call it as radiative forcing, it will be 60%, 60 to 70%. It is only 8% contributing in terms of mass. This is in terms of mass. So that is what you should remember. And as far as radiative effect is concerned, sea salt particle is a completely scattering type, and similarly anthropogenic sulfate is a completely, slightly absorbing type, but mostly it is scattering type only. Black carbon, you can see it is a highly absorbing type. If you illuminate a medium containing black carbon aerosol, 77% of the radiation is going to get absorbed, and that will be utilized in warming the atmosphere. So this is one important point you may remember. And finally, whether aerosol cooling or warming, that is not yet answered yet. Even IPCC report latest one, if you see, there is no clear answer whether aerosols are going complementing to global warming or are they going to offset global warming. There is no answer to that. So this question depends on what is the relative dominance of various aerosol present, which is unknown. So we don't know actually what is it. And in addition to that, after production, aerosols are not existing in the atmosphere as a free species. They are mixed. Actually, it can be mixed in various ways, and these are all complex things which you may not be interested now. But otherwise, multiple interaction between this aerosol, even in an independent species state, is much larger compared to when they are existing in individual species. So this mixing state is another important thing. And if you ask me what is the most fundamental parameter you need for any aerosol aspect, is aerosol size distribution. Aerosol size distribution determines how the number of particles in different sizes are distributed. And this is the simplest form of aerosol distribution. When you plot radius as a function of number, you have only one size. This is not realistic unless you create aerosol in the lab using aerosol generators. And this is a distribution. This is usually called unimodal distribution. If this is a realistic distribution, if you have only one source, only one aerosol source, then you will get this kind of a distribution. And mathematically, you can distribute aerosol size distribution as a log normal distribution function. You are familiar with this. And if you plot it, it will look like this. Different aerosol species, you can plot it like this. And if you have two different sources, for example, you are in an area where industrial emissions are present and you have transportation aerosol also, then you will get a bimodal distribution like this, where you will have two mode radius and two standard deviation. Standard deviation determines the spread of the distribution. And here I represent each source. So you can generate any number of distributions like this if you know the mode radius and standard deviation of different species. And from our lab, I don't know, you have gone to the lab, the same floor, you have an aerosol lab. If at all you have gone there, you can see so many instruments. So this is one measurement from our lab. It is aerosol size spectra. So the next step is, once you measure it, conversion of size distribution to optical properties. That is what is interesting to you. Once you know the size distribution, you may not be measuring, but you have data on size distribution from somewhere else. Then the first thing you have to do is convert it into optical properties, and that will go to radiative properties next. So this is the size spectra. This is size, and this is the time, and this is the number density. How the size is distributed as a function of time, function of wavelength. The reason is the size distribution determines the spectral optical properties because of scattering theory. You know that. As I said, when the the size of the particle is comparable to the wavelength you are considering, that scattering will be maximum. So size distribution has an important effect on optical properties. I will show you in few minutes. And there are several simple terms which you need to know if at all you want to connect aerosol effect to glaciers. I will only talk about the most important thing, which is most essential for you due to the shortage of time. And the most important thing is aerosol optical depth. So you know the Lambert-Beer law here, I is equal to I0 exponential minus E into dx. E is defined as extinction coefficient. And every altitude you have an extinction coefficient, and if you integrate the extinction coefficient as a function of altitude, what you get is optical depth. So for you, most interesting will be the extinction coefficient at glacier levels, not at the surface. Because general belief is that most of the aerosols are concentrated near the surface. You will see that it is not true, because most of the aerosol sources are near the surface, but it is several mechanisms can take the particles upwards. That is what important to you. And optical depth, simply mathematically, if you want to represent it, is integral 0 to h exponent extinction coefficient into dh. So if you integrate it vertically, you will get optical depth. And similarly, single scattering albedo determines the absorption efficiency of the aerosol, and you can define it as the ratio of scattering to extinction. So as I said, black carbon aerosols are absorbing 77% of its energy, and 23% of its is scattered. So that means 23% is scattered, and its single scattering albedo is 0.23, because 0.23 plus the total is 100%, and 23 divided by 100 is 0.23. So that is how you calculate. And one important point you may note from this figure is that mostly people think that whatever is happening in the visible region, that is 400 to 700 nanometer, is mostly important, but you can see that most of the aerosols are absorbing in the IR. This is very important for you when you calculate the warming effect of glaciers, because often you ignore infrared region when you talk about warming of glacier altitudes or even the glacier surface warming due to the deposited black carbon. If you see, the single scattering albedo is 0, means 100% it is absorbing. Whatever energy incident on that is getting absorbed. So from 2 micron onwards, this 4 micrometer and 8 micron to 10 micrometer window channel, where the most of the Earth surface emission is going upwards, this is OLR. If you know outgoing long wave radiation, it is 8 to 12. See the single scattering albedo, it is 0. That means it is completely absorbed. And before I explain scattering phase function, I needed to remind you something. There are two types of atmospheric scattering. One is Rayleigh scattering, when you have particle size much smaller than wavelength of radiation. That is mostly air molecules. Air molecules are much smaller than visible wavelength, and that is Rayleigh scattering occurs. And Mie scattering means when particle size is comparable to wavelength. That is aerosol scattering. Aerosol size, as I said, it is 0.5 or something similar to that. So that in that condition, you have particle size comparable to wavelength of radiation. So you have a Mie scattering. And see the scattering phase function. This is for Rayleigh scattering, when your particle size is much smaller than wavelength. You have equally forward and backward scattering. both are equal. If you integrate, this is incident beam, and if you integrate it forward and backward, it will be same. So that is a characteristic feature of Rayleigh scattering. And similarly, this is the Mie scattering. Your forward scattering is more, but more importantly, when you have particle size much larger than wavelength, you have very complex pattern. So phase function is not very important for you, but single scattering albedo and optical depth are very important. And scattering efficiency factor, how much efficiently it can scatter, that depends on how much efficiently it can absorb, because total is 1. And this is a typical scattering efficiency factor you may need from, you can calculate from any simple scattering model which you need for calculating size distribution to optical properties. I will show in the next slide. And this is a typical, this oscillation is due to Bessel function involved in here, but for you only understand, what you need to understand is that when this number is more, it is more scattering. And what happens inside this red box is Rayleigh scattering, because your size parameter alpha here is defined as 2 pi r divided by lambda. So it is a ratio of size of the particle to wavelength multiplied by 2 pi. So when r is equal to lambda, you have 2 pi. See, when it is 6.28, you have maximum scattering. This is derived from simple scattering theory. So any textbook will give you this plot. 6.28 you will get, that is 2 pi. 2 pi is 6.28. And why you need this scattering efficiency factor is that for converting the size distribution into optical depth. I believe you will get the copy of the presentation, so you don't have to note it down, but this is the equation which you need to convert size distribution which is measured at above Himalayas or any other location. If you have that data, you can convert it to optical depth with this equation. This is extinction efficiency factor, which I already have shown you. And if you integrate its function of R1 to R2 and also height from 0 to infinity, you will get the optical depth. And this NCR is simply the column integrated number distribution, whichever I have shown you in that thing. And if you integrate it already, then you don't have to integrate it further. So you have to integrate only R1 to R2 is equal to. So it is a column effect of aerosol. That is what is optical depth. It looks little complicated to you. I know that. I don't know how much mathematics background you have. But I have to show this because this is how it is, number distribution is converted into this thing. And a simple MATLAB program or a simple program in Excel, you can calculate this. You don't have to write a complex program for this. And in a systematic way, if you want to remember this, estimation of optical properties into optical and radiative properties, you can say that you take a simple Mie scattering model. Now in this era, you don't have to write any program. The standard models are available. You take hundreds of scattering models are available, MATLAB based, Fortran based, or even executable version. You don't have to run or compile also. You take a Mie scattering model, you just input aerosol microphysical and chemical properties, that is size distribution, number density, refractive index, whatever property you have. What you will get in the output is extinction coefficient, single scattering albedo, and phase function. With that, you can calculate the aerosol, how much it can warm at the glacier level, or if you have a layer of black carbon aerosol on the glacier surface, you can calculate how much it can warm that surface, and how it is melting and all. Probably other instructors probably have told you already. But how much is the warming effect of aerosol, you can calculate in this way. The theory behind whatever is going inside this model, I have shown you before, and it is much more than that. Actually, as I said, it is a 6-month course, and it is only very small portion of that I have shown you. But that is the mathematical side of these calculations. But once you have these 3 parameters, at least the 2, you can calculate the warming effect of aerosols. And simply I can tell you in a general way how aerosol impact climate. If somebody asks you how aerosol impact, then the simplest way is it is directly and indirectly. There are 2 ways aerosol can impact. And directly by scattering incoming sunlight back to space, because as you know aerosol can scatter. So part of the scattered light is going back to space, and partly by absorbing sunlight. And indirectly aerosol has the ability to act as cloud condensation nuclei, and thereby it can modify the properties and lifetime of clouds. Why lifetime of clouds? Because for a given water vapor content, if you have more aerosol, you will have large number of small cloud droplets, and if you have less number of aerosol, then you have a small number of large droplets. So the probability of raining is more in the second case, when you have less number of large particles, because particles need to grow to some size level before it can rain. So the lifetime of cloud is affected when you have a large number of particles, because there will be competition for the available water vapor. So available water vapor will be divided into all particles together. So you will have a change in the lifetime. Lifetime of the clouds will be prolonged, or the number of cycles cloud has to undergo before it can rain, that is non-precipitating cloud cycles will be large. So it can increase, usually it is 4 before a cloud rain. It undergoes a non-precipitating cloud cycle of 4 times, and it can change it to 9, 4 to 9. That is what simple model calculations are indicating. And for short wave radiation, that is wavelength below 4 micrometer, this is called direct radiative forcing, not the cloud radiative forcing or aerosol cloud interaction. This is the direct effect because of scattering and absorption. You have a scattering and absorption in the atmosphere due to air molecules and aerosols. And there are two main effects. You have an increase in the reflectance, and also you have a reduction of solar radiation at the surface. These are the two major consequences of direct radiative forcing. That is mainly for wavelength less than this. And net effect of cooling or warming is not known, because we don't know the refractive index or what is the composition of aerosol. And for the long wave region, you can see that mostly it is absorption. Why? Because your scattering effects are very small. Long wave radiation is much longer than size of aerosol. Size of aerosol particle is 0.5 or less. But long wave radiation, especially window channel, is about 10 to 12 micrometer. So that is about 20 times longer or larger than size of the particle. So you don't have much scattering effect. It is very less. It is there. But the main process in the long wave radiation, long wave region, that is lambda above 4 micrometer, is absorption. So that the energy is coming from the earth, because not mostly coming from the sun, because long wave radiation is emitted by the earth, and that decreases the earth emitted radiation because of absorption. Aerosol present in the atmosphere can decrease the long wave radiation going from the earth and increases the ground reaching long wave radiation. The reason is it absorbs substantial amount of short wave radiation while the sunlight is coming from sun to earth surface, and it re-radiates in the form of long wave radiation. That you know from Wien's displacement law in radiation, if you remember basic radiation laws. Once it is absorbed in the atmosphere, atmospheric temperatures are very less, so whenever it is re-radiating, the wavelength will be in long wave region. So that way it contributes to an increase in the ground reaching radiation here. And whether aerosol will cool or warm the planet, it started from around 1982. If I remember, this is the time, I was a student at that time, this is the time the debate started where aerosol can cool or warm the planet. So that era, what we have learned from volcanic eruption is that volcanic eruption can inject large amount of aerosol. This is all aerosol, ash particles, and that can go to the stratospheric altitude, that is about 15 to 20 kilometer higher level, and there was a cooling effect because of that. And only difference compared to that time and now is that now that time this was the major source of aerosol, because there were no much industries or large number of vehicles. Now you have a large number of vehicles and industries or biomass burning emitting black carbon aerosol, and that time this is mostly, see, you can see that it is white. Whatever is looking white, that means it is scattering. If it was not scattering, you will not see it as white, it will be black, then it will be absorption. So clearly you can see that. So at that time the belief was that it can cool the planet, and this is the process. There was an volcanic eruption here, and that inject large amount of aerosol into the stratospheric altitudes, and if you know the circulation pattern at the stratospheric levels, it is so well mixed, irrespective of political boundaries. So once it goes to stratospheric altitude, this is what happens. It completely mixed the globe. So it covers the entire globe in a matter of 3 months. So this is about 3 months. You cannot see the time frame, but it is about 3 months from the time of volcanic eruption. So it can cool the entire planet. So that is what we learned at that time from volcanic eruption. And you can see that from this simple equation. This is the simplest way we can write the Earth energy balance equation. You probably heard from somebody else before. This is the energy from sun, that is solar constant, and this is divided by 4 because of day-night differences, and only one side of the Earth is illuminated, but it is emitted from 4 pi r square, the total surface area of that, you probably know that. And 1 minus alpha, alpha is the reflectance of the planet, and sigma T raised to 4, you know, it is Stefan-Boltzmann law. If Earth radiating temperature is TE, then sigma T raised to 4 will give you the total energy emitted from the Earth, and this is incoming radiation received by the Earth. And alpha is the reflectance of the planet. Typically it is about 0.3, including clouds, aerosol, surface, ocean, land, everything together, ice, it will be about 0.3. And aerosol have a significant influence in determining the value of alpha, this albedo, and has consequent impact on the climate system. So on a global scale, if you want to calculate how much is the warming or cooling effect of aerosol, simply change the value of alpha and then calculate how much temperature will change. You can do it in a calculator. Simply you calculate a calculator in your mobile phone. You calculate how much T is changed if you change the reflectance value from 0.3 to 0.31. You will see a substantial amount of change. So aerosol can affect this value of alpha substantially. I will tell you how much. And if you have any application which you need to do the radiative forcing, that is how much aerosol is affecting radiation, then I can give you 2 equations. This is for only purely scattering aerosol. You don't have to note down this equation, any textbook you will see. So this is the simple radiative forcing equation. This is solar constant and the parameters are given, and cloud fraction, surface reflection, backscatter fraction, everything is given. It is an old equation. This equation you can use to calculate, and for absorbing aerosol, you can see that this is aerosol effect. How much aerosol can affect the radiation? And for different single scattering albedo values, that is absorption efficiency of aerosol, you can see that as a function of wavelength, optical depth, this is drastically changing. For an optical depth of 0.5, you have about 30-40 watts per meter square. It is a very large amount of energy. If you convert it into temperature following the methodology I have told you, it will be very high. It will be quite high. And indirect effect. And this is the best example of how aerosol can act as cloud condensation nuclei. So this is industrial aerosols are going up, and sunlight is heating the surface of the surface, and then once aerosols are going up, transported upwards, water vapor will condense on that, and it will be acting as cloud condensation nuclei. And then that is the simple way you can tell what is the indirect effect of aerosol, but that is not true. Simply we cannot say that more aerosols are there than more cloud droplets and all. See the thing here, this is a biomass burning area, and this is an volcanic aerosol region. This is an volcanic eruption here, and this is the trajectory of the volcanic plume, and mostly sulfate aerosols are coming from volcano, that is scattering aerosol type, and it cannot warm the atmosphere. It can only cool the atmosphere. But biomass burning, it is mostly black carbon aerosol, and there will be intense swarming due to black carbon aerosol, and you can see that along the trajectory of this volcanic eruption you have cloud cover. But at the same time, where biomass burning is there, that is a cloud covered area, but that place there is no clouds. That is because the intense warming due to black carbon here, it evaporates clouds. So it can reduce the cloud cover by half. That is what model calculations are indicating. Yeah, but this is only clouds. Rain is even more complicated than that, because even the cloud cover it can affect, and the rainfall mostly is influenced by the size distribution of aerosol which create the clouds, which is participating in the cloud condensation nuclei process. So if you have, as I said before, you have a large amount of large particles, then your probability of raining is less. And if the number of particles are less and the particle size is also very less, then you will have small number of large particles and probability of raining is very high. So that is actually next process. Once aerosol acts as cloud condensation nuclei and cloud has to form, and then the question comes whether it will rain or not. So the probability determined by size distribution, aerosol size distribution. But this process, warming or cooling, and which is consequent effect on cloud formation, is because of the refractive index. Actually that determined by the chemical composition. And this is the most recent questions which our climate change community is trying to address. What are the impacts of anthropogenic aerosol on Earth's climate? And is aerosol forcing similar in magnitude to that of greenhouse gases? And what is the impact of aerosol on cloudiness? And can aerosol alter hydrological cycle or not? And can black carbon aerosol impact glacier melting? And many more. I can put almost 50 to 100 questions like this, or even many more, because most of the things are unanswered. There is no answer to any of those questions, even though some papers, often Nature or Science journal, they will tell some answers, but they are all incomplete. In my opinion, that is not complete study, it is incomplete study. And now that completes the first part of my lecture. So this is what you need for as a background to understand the importance of aerosol, and some beginning into yes, please. It is done, but thing is, they are developing countries are, because I was in IPCC, I witnessed to all this discussion. Developing countries are emitting CO2, and they are dominating. In whichever way you say second, there is always a thing that second to only, after US and China, US, Europe, China, then it is India. But it is simply like if the student is getting 100 mark and the second student getting 1 mark, he is still second. Data is there, but then I have to make a strong statement for that. There is a saying in my native language, maybe it is in English also. It is easy to wake up somebody sleeping, but if somebody is pretending sleeping, how you will wake him up? It's not possible. So they know that whatever the fact, it is not that developing countries are unaware of this. They know, what I understand is that they know the fact, but for their convenience, what they will have to do, they will have to lose this luxurious life, air conditioners, one family, 10 cars, all those things they have to get rid of. Lifestyle change they are not willing to do. Especially US and all publicly told that we are not going to change the lifestyle, you change. many times. It is said in the public forums. Not November this year is very important. Paris, next climate change conference is going to be in Paris. COP 21 or 22. That is very important. I don't know what our country is going to do. And now I come to some of the observations which we are making, again which is relevant to glaciers, because we make lot of experiments, but I will cover only, there are some unknowns, vertical distribution of aerosol. Without that you will not know how much fraction of aerosols are reaching the glacier levels. And state of aerosol mixing is less important, but size distribution and shape is more important. But the first thing is most important, because whether the surface aerosol can go to glacier levels. And this is the network of observatories maintained by Indian Space Research Organization. And these are the recent sites which is shown as pink. All other things are running for almost 20 to 25 years from now. So the database which I am showing is mostly from these sites. And this network of aerosol observatories shows that it is all India average aerosol optical depth, which is a measure of aerosol concentration over India. And it shows that aerosol concentration in India is increasing at a rate of 2.4% per year. So if this rate of increase continues in the current rate unabated, then by 2050, around 2048, your aerosol optical depth is going to double and it approach unity. See this Lambert-Beer law? From this equation you know that when it is unity, m you take 1 for now, that means you have exponential reduction of surface reaching direct solar radiation. It is about 67% of radiation is depleted before it reaches the surface, if you ever reach it to this. But it's possible that government can take other measures, pollution control measures, and control it. But the current rate from 1980s to 2010 to 2015, it is that trend. So if 30 years nothing has happened, then I am not sure whether something will happen in this period also. Then it will follow this trajectory. It is going to be very difficult then. And I am not surprised by that, because growing cities, ever increasing urban population and traffic, and rapid and unplanned industrialization. So these are all, see the number of vehicles going from that 1950s to the, now it is very, very high, and to 200 million vehicles by 2015. So the same thing with industries or anything you take, real estate sector, everything is going very high. So it is not surprising that amount of aerosol going up. And if you want to correlate it with glaciers, Professor Kulkarni has studied a lot of areas in glaciers, and this is a 2007 data. What he said is that there is a 23% reduction in glacier area from 1962 to 2002 or 2003. 23% reduction, and there is a five-fold increase in the aerosol concentration. If you correlate the two, you will get a perfect negative correlation. But whether this is the cause for this, we don't know, because you probably heard from all other speakers that it is not simple. It is not that you take an ice piece and warm it, it will melt. It is not like that. A lot of mass balance calculations are involved in that. So it is not possible to say that this is responsible for that. But still, this is an observation I want to show you. And the most important question you needed to understand is that, can surface aerosol reach higher atmospheric level? If so, how? I will try to address in few slides. One example I can tell you. This is Nainital. I hope some of you have gone there. We have conducted a major field campaign with the help of ISRO and Department of Science and Technology there. See the top of one of the hills, it is called Manora Peak. This is the lab, IRIS. It is under DST, and this place we have conducted an experiment. And this is a close-up of our instrumental setup at that time. So what we have seen is we had a simultaneous measurement at the surface of the Himalayas and also at 2 kilometer altitude above. And what we have seen is from morning to afternoon hours, there is a transport of aerosol from the surface to top. See here, it is only up to 2 kilometer altitude, but by about 1 to 2 o'clock you have it is going. This is aerosol actually, this is LiDAR measurement. It's a laser beam. We send a laser beam and measure aerosol. It is going up to 4 or 5 kilometers. So it can reach further also. This is only an example. This is the location and this is the actual values you can see. It has reached more than double by that time. And the advantage of this location is that this is Nainital, and when you come few kilometers down, it is 300 meters. So it is like a vertical, it is like a wall. I have gone in vehicles, so you can see it is like a wall. By the time you reach 200 meters, 2000 meters, it is vertically down. So it is a best location to study this kind of transport from the Indo-Gangetic basin, whether such aerosol can reach glacier level or not. So the best way to study this is using pollution dispersion model. So this is a pollution dispersion model we have used. And the question we were trying to address was boundary layer dynamics. Because you know that morning boundary layer height, atmospheric boundary layer height, I don't know you know atmospheric boundary layer, this is lowest layer of the atmosphere. It increases its height from morning to afternoon hours because of heating. Once you heat the earth's surface because of solar radiation, the boundary layer height, because of the heating, thermals will start going up because hot air will rise, and that is not the reason for boundary layer, but it can carry particles to higher levels. So when inversion is not there, see this model simulation shows that it can go very high altitude, up to 4 or 5 kilometers, easily it can take these particles up. And we have conducted a instrumented study when we have fixed instruments in a van, and we have taken this instrument from the surface of Himalayas to higher altitudes. So what we have observed is that black carbon mass concentration we have measured from 300 meters to 2000 meters, that is from Pantnagar to Nainital. And what we have seen is that during morning hours, most of the aerosols are confined to 500 meters or 1 kilometer. But afternoon hours, you can see that it is gradually going up. It is climbing. And that is also supporting with the fact that summer season, we have very high aerosol optical depth and at 2 kilometer altitude, and winter season we don't have, we have very, very low. This is like almost background level. So that is also supporting our measurement. So we have done concentration weighted trajectory analysis extensively, and what we have seen is that in winter 32% of surface aerosol from Indo-Gangetic basin can go to glacier levels. Glacier level is taken as 4 kilometers here, but it is not exactly say correct, but 4 kilometer we have used here to determine the glacier level. 4 kilometers or above, 32% of the aerosol can go up. And during summer season, 67% can go up. But then if the boundary layer dynamics is the reason for taking particle from surface to higher altitudes, how 32% can go in the winter? That is a very important question we were surprised. Because boundary layer dynamics is not playing any role in winter because it is very cold season, and boundary layer is only up to half kilometer or around that. So there are mechanisms other than boundary layer dynamics which is playing, which is carrying this particle from the Indo-Gangetic basin to higher levels. So to examine that, we have conducted extensive aircraft-based studies. Indian Space Research Organization is maintaining an aircraft in Hyderabad, NRSC aircraft. We have used that. They were kind enough to give us almost 300 hours of flying. So we have done extensively, and we have gone all over India. And what you can see is that most of the aerosol during pre-monsoon, they are located at a higher level. That is about 3 to 4 kilometers, not at the surface. So we call it as elevated layers. And more than 70% of aerosol was found above clouds. And if aerosols are found above clouds, then the difficulty is clouds present below an elevated aerosol layer act as a highly reflecting surface. It is like a mirror placed below the aerosol layer. So if a mirror is placed or cloud is present below an aerosol layer, most of the energy is reflected back and interacting with the aerosol, and absorption can be 3 times larger compared to a clear sky condition. So that is what is happening here. So in addition to that, our satellite remote sensing measurements shows that you know that pure dust is non-absorbing. There is nothing in dust which you can absorb. But if dust is contaminated with black carbon, its absorption efficiency is much, much higher. As I told before, that mixed aerosols are much more dangerous than individual aerosols. So this is what happening here. So then another thing you will have to worry is this deposition of contaminated dust on glaciers. It will have much more impact on, we know that dust is depositing on glacier level also. And one striking feature we found from our aircraft campaign from southern India to northern India is that over southern part of India, most of the aerosols are below clouds, and as you go north, this is about central India, you see that 4-5 kilometer also you have a substantial amount of aerosol reaching the higher levels. That is more dangerous as far as glaciers are concerned. And you take a Calypso satellite, you know, which is the best thing for vertical distribution of aerosol, because aircraft we cannot fly throughout the year and study that. So if you want to know the complete annual picture, see the December to February, March to May and June to September picture is given. You can see that winters it is not much going higher altitude, but summer season, March, April, May, you can see that it is very high. It is going up to 5 to 6 kilometers. Aerosols are, any satellite data you take, you will see this image. And this is the consequence. If this is true, you have absorbing aerosol over northern or central part of India, and fraction of its above cloud is very high, then it can trigger dry convection and air will go upward and dragging the air from the southern part of India to the north. Because when you have vacuum here, the air circulation will be changed like this. So a substantial amount of circulation change can happen as a consequence of this. And our Director General of Civil Aviation did not permit us to fly our aircraft above 3 kilometer or 4 kilometer, because we had so many instruments and protruding outside the aircraft. There are sampling inlets like that. So we have used this balloon facility. This is high altitude balloon facility from Hyderabad, and we have measured up to 9 to 10 kilometer altitude with this facility, because we had no other option to measure. So this is the payload we are sending, and up to 10 kilometer you can see that 4 to 5 kilometer your BC is very high, and even at 8 to 9 kilometer altitude you have very large elevated layers. This concentration, I can tell you that 2 to 4 microgram per meter cube is comparable to what we measure at this location. So you have black carbon concentration at this level is comparable to what we measure in Bangalore. So see the consequence of this. It will be substantially dangerous to glaciers as well as climate. And this is the self-lifting hypothesis which many people are now trying to study. So this hypothesis says that once you have black carbon aerosol layer at a higher altitude, at the surface you cannot do that, because atmosphere is so thick at the surface, you cannot warm it. So if you have a BC layer at, similar to the one I have shown you at 10 kilometer altitude, it can warm the layer substantially and trigger dry convection, and it goes up and then again form another layer at some higher height, and it can go from there. So that means once you trigger the black carbon due to some mechanism, whether it is boundary layer mechanism or some other mechanism, to some level, it can go up to the stratospheric altitudes. That is what this hypothesis is saying. So we don't know, but there are some validation studies made on this. Some people tracked the smoke plume from Australia bushfires, and they have seen that 15 to 20 kilometers and also thousands of kilometers away from the source region, this black carbon particle can reach. So Indo-Gangetic Basin is so close to Himalayas. So if that is true, if self-lifting hypothesis is true, then it is very easy that black carbon particle can go up at the higher levels. And this is the consequence of particles at higher levels. As I said, the reason is its atmosphere is dense close to the Earth's surface and thin at higher levels. For a given amount of absorbed energy, which is same, for a given aerosol layer it is same, and warming is much more at higher level. You can show it in the help of a simple radiative transfer calculation. Same aerosol layer, see here the same properties, same optical depth and single scattering albedo. It can cause a warming of 0.5 degree Kelvin per day near the surface. If you take this layer to 6 kilometer altitude, that is glacier levels, your warming will be greater than 3 Kelvin per day. That is quite high. Same aerosol layer. Due to some mechanism, you take it to the higher level, see the properties are exactly same. And this is the equation for warming rate. And there are two issues we have to address here. Intense aerosol induced warming at glacier level, whether it has any impact on glaciers or impact on stratospheric ozone layer. That may not be interesting to you, but it is another global issue. And to summarize, one natural processes, sedimentation is there, gravity, action due to gravity, and it is very slow process. But rain out is very fast. Once you have rain, then it cannot be removed. Yeah. Yes. Once they are above clouds, what happened is the reflected radiation from the clouds, it will amplify the warming by a factor of 2 to 3. And then from that point onwards, it will be elevated by its own. That is what we see. Once you have coated aerosol, your absorbing efficiency is a factor of 3 larger. So if you have mixed aerosol, it is the most dangerous combination you can have. And this is what the summary of what I have said. During the summer and pre-monsoon season, most of the Indian region is characterized by the presence of elevated absorbing aerosol, which may not be a good news for glacier studies. And unexplained absorption makes aerosol impact assessment a challenging task, and it may be unrealistic as on now. And build-up of aerosol over Asian monsoon regime can be a source of aerosol at glacier level. It is possible. We don't know, we don't understand it fully, and it may have an impact on glaciers. And there are several questions we can ask: how aerosol affect Asian monsoon rainfall? Can aerosol intensify tropical cyclone? What fraction of surface aerosol can reach glacier levels? Similarly, there are so many unanswered questions. So finally, what I can say is that crucial question to be answered to tackle aerosol climate impacts are so many compared to what is known. Thank you. Questions? It will be different because PM is surface level. PM 2.5, what you are saying, is aerosol below 2.5 micrometer in size. That is measured at the surface level. AOD is a column integrated property that determined by the surface to the top of the atmosphere. So it depends on how it is vertically distributed. So it can be different for Bangalore, different for Mumbai, Delhi. Then no doubt European countries it will be different. No, the best thing you should do is take Calypso data and take the vertical distribution and you scale it down to surface and then compare. Without the knowledge of vertical distribution, you cannot correlate PM 2.5 with AOD. Thank you.